Okay, this is going to be a recap of everything you've learned, everything you need to know for the log test. It's also a great way to review for finals because it's going to summarize everything that you need to know. Okay, first of all, exponential graphs. If the base is more than 1, that means that it's going to grow. When you have an exponent, you're going to plug in the number 0. 2 to the 0 is 1. And plug in the number 1, and then you get 2. This is exponential growth. We have the point 0, 1, 1, 2. It starts off like this and goes up, 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 up. They are asymptotic to the x-axis. Exponential decay is also asymptotic to the x-axis, but instead of growing up, he's going to be coming down. If your base is less than 1, that makes you decay. You still plug in 0 and get a 1. We plug in -1 and we'll get a 5. If you plug in 1, you'll get 1/5, but I like having both. 0, 1. -1 starts you up at 5. +1 is just 1/5, so I could see that it's definitely getting smaller, 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 but it's never going to be 0. It's just going to be a really small fraction. Okay, so in general, exponential graphs are asymptotic to the x-axis. Numbers you should think about plugging in. You should plug in 0 and then plus or -1 depending if you're growth or decay. Exponential graphs, make sure you know them. Okay, we also studied logarithmic graphs in this chapter. Okay, remember we cannot take the logs of 0 or negatives. Okay, so that's going to affect our graphs. No graphs on the left-hand side. When you have a base that's 5, they're going to be growing. Let's plug in the number 1. Log of 1 makes 0. Let's also plug in the number 5, the same number as the base, and you'll get 1. Logarithmic graphs are asymptotic to the y-axis. So we plug in 1, we plug in 1, 2, 3, 4, 5, we get 1. So they start close to 0. Don't touch 0, you can't take log of 0, and shoot over to the right. Okay, let's take a look at this. We're still going to plug in 1. Log base anything of 1 makes a 0. I could plug in 1/3, but maybe what would be better is plugging in a 3. 1/3 makes a 1. A big number 3 would be easier to graph, but that's going to make -1. All right, let's go ahead and plug all of them in so you get a good picture. 1, 0. 1/3's way up here. 1, 2, 3 is -1. Okay, asymptotic to the positive y-axis, and then shoots off to the right like that. So, log graphs, in summary, are asymptotic to the y-axis. Points that you should try to find. Always plug in 1 and you'll get a 0, and then plug in a number that is related to the base. Either same as the base or reciprocal of the base, so you can find another easy point. Okay, what else do you have to know? This entire chapter, we switched back and forth between inverses, between exponents, and logs. The inverses of exponents are logs. If you're stuck in a log, then switch to exponent. If you're stuck in an exponent, switch to a log. Logarithm. Inverses are reflections of each other over the line. Y equals x. Let's go ahead and graph that line, y equals x, right away. So our graph will reflect up and over that line. Okay, on the left, I see an exponential equation. Let's just separate this. This is exponential growth. Let's find some points we can plug in. Let's plug in the point 0. Plug in 0 to get the point 0, 1. Plug in 1 and we'll get a 3. Does he have an asymptote? Which axis is it going to be? Yes, the x-axis. All right, now let's talk about the log. This log equation is definitely going to be growing. He has the point 1, 0. He has the point 3, 1, and is there any asymptote? This one's going to be the y-axis. All right, let's color code these here. The exponential growth. 0, 1, 1, 3. Asymptotic to the x-axis, going up, up, up. The log graph, remember, you cannot take log of a negative, so sometimes I even just cover it up with my hand. I'm going to plug in 1 and plug in 3 and asymptotic to the y-axis. He's going to go like that. Perfect. They are reflections of each other because they are inverses. Okay, let's practice some transformations with our graphing. This is exponential. And maybe what we'll do here is graph a basic. Let's graph y equals 4 to the x. In black, let's just graph a basic, and then I'll graph one that's been shifted. Okay, so first, let's graph this one, which has special points 0, 1, and 1, 4. 0, 1, 1, 2, 3, 4. He's asymptotic to the x-axis. He's going to shoot up like this. Oops, okay. Now it's time for the real graph. The real graph right here has a transformation. If that 2, minus 2 is near the x, that means 2 units to the right. Okay, so everything about this basic needs to go 2 units to the right. The asymptote, which used to be on the x-axis, gets shifted to the right, so nothing really happens to that line. This point right here needs to go 2 units to the right. This point here needs to go 2 units to the right. So it's still exponential growth, except he's 2 units to the right of what he used to be. Okay, let's do the same thing over here with this log graph. Let's graph a basic. Let's graph y equals log base 2 of just x, and then we'll do some shifting. So let's graph this basic right here. This is the basic one. Some special points could be 1, 0, 2, 1. Log graphs are usually asymptotic to the y-axis. So we've got 1, 0, 2, 1. Here's the log graph. Now let's talk about the real one. The real one right here has a couple transformations happening. Inside by the x I see 1. That means 1 to the left. I see minus 2 outside after it. That means 2 down. Okay, let's shift everything about this graph 1 left and 2 down. The asymptote needs to go 1 to the left and 2 down. But 2 down really doesn't affect the line. The line goes forever. Let's take this point right here. We're going to take it and go 1 left and 2 down. This point right here needs to go 1 left and 2 down. So now we have our log graph. Make sure you're asymptotic here. It's good we drew that asymptote. Up, 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 and away. And in general, it should look 2 left and 1 down from the basic. Okay, drawing little basics on the corner of the test might be a good idea so you can look at the shifting ones with keeping your eye on a basic one. Okay, what else did we study this chapter? Lots and lots of solving. Let's practice all the different solving skills that we learned. Can we make common bases with this? Well, not really, because they're different. And we got 3 terms. So I think this is a good time to maybe use an A substitution. You have to say on your paper, let A equal something. I'm going to be replacing e to the x. So this equation has e to the x. But this one actually needs to get moved downstairs to become e to the x. So let's substitute a in the correct places. A minus 1 over a, and then I'll minus 6 to equal 0. Okay, we can't solve it with this denominator, so let's put some big brackets and multiply the entire equation by an a. So that gives us a squared minus, careful right here, minus 1 minus 6a equals 0. Let's write this in descending order and pray for some factoring, but I don't think our prayers are going to get answered. So we're going to have to do quadratic formula. Let's do the quadratic formula and let's make sure we say a equals 6 plus and minus the square root of 36 minus 4 times negative 1, that's going to become plus all over 2. So A is 6 plus or minus. Can radical 40 be simplified? Yes. What's going to come out? 2 radical 10. I'm going to give them each their own denominator so we can cancel this nicely. So A is 3 plus or minus radical 10. Oh, wait a minute. Time for A to go away. A was e to the x, so it's time for this to come back in. E to the x equals 3 plus or minus radical 10. You cannot leave x in the exponent like that. We're going to have to switch to a special kind of log called the natural log. Log circle, I'm going to have to put all this stuff right here into the of. And it's time for me to think to see if both of them, I know the positive one's going to be okay, but you don't want to have an of that's negative. Radical 10, I know radical 9 would make a 3, so this is 3 point something. 3 minus 3 point something, that is not good. So the only answer here is natural log of 3 plus radical 10. Wow, look at that answer. Okay, let's practice some more solving. Number 2 looks interesting. I don't know. Do I have to make A's? Let's rearrange and simplify and see if I'm going to need to use an A. Okay, let's see what we could do here. I know I can write this as 3 power to a power is very powerful. That's going to be multiply 4x times 3 to the x squared. And if I bring this 3 upstairs, that would make his exponent positive. Okay, you kind of do some baby algebra as much as you can, and if you realize you're stuck, then you can use an A. I can do more, so I'm going to hold off. If the bases are the same, what do you do to the powers? It's not a power to a power. We're just going to add those. X squared plus 4x. I switched it around so it'd be descending order. Oh, look at that. We've got common bases. So we do not need to use an A substitution here. I can just say, since the bases are equal, the powers are equal. X squared plus 4x equals the 12. Since it's quadratic, we'll move everything to the left. And does this factor? Oh, it does. It does. X and x. How do we make a negative 12? Plus 6 minus 2. So I think we have negative 6 as an answer and 2 as an answer. Now let's think about it. Do we have to check these? I look at the original problem and it wasn't a log problem. Exponents are okay. If it's not a log equation, you don't have to worry about throwing away the extraneous and looking at negative ofs. So both of those solutions are going to work. All right, let's do some more e's. Let's do as much work as we can to see if we can work with the bases since I see a lot of e's. On the right, I'm thinking I want to bring this one upstairs. E to the x times e to the negative 3. Once again, I see common bases that are being multiplied, so we can go ahead and combine those e's into a single e. And what should we do to those exponents? Add them or multiply them? Yep, we're going to add them. X minus 3. Oh, look at this. We got some more common bases. Since the bases are equal, then the exponents must be equal. So negative x squared equals x minus 3. I'm going to move everything to the right to solve this one. Okay, 3, does not factor. Okay, let's do the quadratic formula. I'm going to start off with what letter? X. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative 1 plus or minus the square root of 13 all over 2. Well, that's just x directly. There's no substituting anything back in, so I don't have to worry about an A trick or substitute. It's not a log problem. These are both good. These are both good. Okay, let's keep going down here. Number 4. Let's solve a log problem. I see a log, and I see x's are stuck in the log. There's no log over here, so I can't just divide by log and get that. I can't just make that go away. I cannot work with it like that. I'm going to have to do a log circle. 2 to the power of equals that. So 4 equals x squared minus 2x minus 31. Once again, a quadratic. I'll move everything to the right. Make it minus 35. Does this factor nicely? I believe it does. X, we'll need a negative 7 and a positive 5. So we've got two answers here, a positive 7 and a negative 5. Are both of those going to be okay? This is a log equation. We have to check. That's the number that goes in that cannot make a negative of. But 49 minus 14 minus 31, I think that's going to be okay. And then negative 5 squared is 25. Negative plus 10 is 35. Oh, that's going to work. They're both good. You look at the original equation. All right, we're going to continue on here. Number 5. Oh my goodness, there's so many logs. You cannot say that x equals this because there's too many. If there was one log and one log, then you could isolate the ofs. So maybe we should think about combining some of these logs. Can two logs be combined into one log? Absolutely. What are you going to do to the ofs when they're being added? The ofs get multiplied. X squared minus 4x. Write the rest of the problem equals natural log of x plus 6. So this would not be a good time to do a log circle. What we're going to do here is look, because you have a log on the left and a log on the right, we're going to match things up. That means their ofs must be equal. So you just write x squared minus 4x equals the of on the right. That's not a log circle. This is a good technique when there's two logs, one on the left, one on the right. Let's move everything to the left. And does this factor? Oh, I think it does. X and x, a negative 6. I'm going to have one of them be negative, negative 6, and then positive 1, and then that would add to make a negative 5. So x equals 6 and x equals negative 1. Wait, I should check to see if these are both good solutions in the original problem. I'm a little worried right here where it said natural log of just x. So we cannot have negative 1. Is 6 going to be okay in all the places? Yes, that one's okay. So we ended up with one solution from that equation. Okay, number 6. Let's do some baby algebra. Anything we can do to get x, we have to isolate the x. So I can divide both sides by 18, and that would be getting closer to solving for x. It's okay if there's a fraction on the right. Can you do any more baby algebra? Got to get to that x. But he's stuck in an exponent. When you're stuck in an exponent, what do? You switch to log form. Let's do a base of 2. Log base 2 of 7/18 equals x. A quick log circle will help to see if that came out right, and we're good. Okay? It's okay to have an answer that looks like that. That's going to be an irrational decimal if you were interested in typing it in, but that's exact, so we're going to leave it. Okay, we also studied how to find domain this chapter, and that helps us draw graphs and stuff a little bit. So the first thing we have to do is remember that when you're doing domain, the of must be greater than 0. So you just look at this expression right here, and that's the thing you have to solve. X plus 5 over x minus 9 needs to be greater than 0. Now we did study this in chapter 4. You cannot multiply, Can I cross multiply? The sign might flip. How do you solve a rational inequality? You're going to have to use a number line. Okay. Do we have a 0? Okay, that means we're ready to start. What numbers go on the number line? We've got -5, +9. Okay, great review for your final here. Do we ever bubble in the number from the bottom? Absolutely not, because that's the denominator, and that would make a 0. Can we bubble in the -5? Well, that depends on the sign. Since this is greater, we'll leave it open. And now it's time to test. So let's test -10. Does that make positive? I believe it does. So we're going to go ahead and fill this in. How about 0? 0 makes negative. That's not what we want. How about 10? 10 makes positive. That's what we want. Okay. So the domain for this equation is -infinity to -5 union 9 to infinity. Domain of that log equation. Oops. Okay, let's do another domain problem. This domain, this log graph right here has an of. It's got a lot of fancy stuff, but all you really care about is the of. I know it's got +11, it's got a 17. That's nothing to worry about. You cannot take log of negative. The of has to be positive. Okay, how do we solve quadratic inequalities? Oh, this is chapter 2, and this is on your final for sure. So what we can do here is factor this into x plus 2x minus 2. Now, we're not going to do anything silly like say it's greater than +-2. That's silly. We're going to draw a number line. We're going to put -2 and +2 on the number line. Open or closed bubbles? Some open bubbles, you say? And it's time to test. Is -3 going to come up positive? Yep, that'll come up positive. How about a 0? 0 makes negative. That is no good. +3, that makes positive, and that's going to be good. Now, there's another way we could also do this. When you have a quadratic inequality, you can factor, and you could put your critical points on a 2-dimensional graph instead of a 1-dimensional. So we've got -2, +2, open bubbles again. And then I would ask you, do you know what this graph looks like? A parabola shifted 4 units down. Okay, so you could draw a parabola like this if you'd like. You can think about the parabola graph, but you still have to think about where is he greater than 0. He's greater than 0 here and here. So either way, you're getting the same answer. Let's go ahead and state the domain for this log equation. From -infinity to -2, union 2 to infinity. Okay, either way, I would need to see a 2-dimensional or a 1-dimensional graph. Okay, let's do some more solving here. I see the x is in the exponent. So I think we're going to have to switch to a log, a natural log. A natural log of 1/3 equals -2x. Okay, we're getting there. The only thing we need to do to get x isolated is divide both sides by -2. So x equals natural log of 1/3 divided by -2. Now it's time to clean that up a little bit. All right, what am I going to do? I'm going to take this negative and I'm going to write it in the numerator instead. So I'm just taking the negative from the 2 and writing it on the natural log. Okay, you don't ever want to leave negatives downstairs. And it's actually going to clean this up really nice. The -1 out in front can go up as a power. So I'm going to put the -1 as the exponent on that 1/3 fraction. Now, what does a negative exponent do? It's going to reciprocate that number. So we can have an answer of 1/2 times the natural log of 3. That is the same as this. It's just a lot cleaner. So I hope you're able to follow what I did there. and maybe think about doing stuff like that in the future. Okay, our last equation here is to solve for x. You have to really look at these problems carefully to see how many logs you have and how many terms you have. Okay, we can't just say these ofs are equal because there's a 1. There's 1, 2, 3 terms. So I'm thinking, let's put all the logs on one side at least. Let's put all the logs on the left. So minus log base 8 is going to go to the left and become plus log base 8 of x plus 4. And we still have that 1. Okay, at least they're together. Maybe we should put them together even more. Can 2 logs be combined? If the bases are the same, they can be. So I'm going to write 1 log with a base 8. And what shall I do with those ofs? Let's multiply them together. X squared plus outers and inners makes 10x plus 24. And now, how are we going to get that x out of the of? Since this is a log, you cannot just look at this stuff. We're going to have to change from log form to exponent form. Let's use a log circle. 8 to the power of 1 makes 8 equals x squared plus 10x plus 24. Let's move everything to the right. X squared plus 10x plus 16. Let's go ahead and factor into x plus 8 and x plus 2. So there's 2 solutions here, negative 8 and negative 2. Oh, but wait. Let's check to make sure that both of those are going to be okay in the original problem. Is negative 8 going to work? Nope. Does negative 2 work? He's a negative, but when you plug him in, the of stays positive, so he is the only solution. Don't just cross off the negatives right away. Okay, good luck studying for this last test of the semester. Bye, guys.